Now we go to another strengthening mechanism, namely solid solution hardening. Most metallic materials are not used as single elements, but rather as alloys, which means that one or more other elements are added during the production of the material. Those alloy elements can fit into the crystal structure in different ways. We see here on this picture that we have added in the top part, that means atoms that are smaller than the base materials atoms. And in the lower picture we have added alloy elements that has a larger atom size than the mother lattice. And what we see is that we will get some stresses around these atoms, both if they are smaller or if they are larger. And if you look into what may happen when a dislocation is moving close to these alloy elements, we can see here that it will start to interact with the alloy elements. As the alloy elements is a disturbance in the crystal lattice, and also the dislocation is a disturbance, it means that they tend to cling to each other, and in that way they can minimize the total disturbance in the system. So alloy elements tend to line up and decorate the dislocations, and in that way they also kind of lock the movement and the slip of the dislocations. It happens both for smaller atoms and for larger. Of course, the effect of this is dependent on the size or the size differences between the alloying elements and the base materials atom sizes. If they have a big difference, we will have also larger effects, and the hardening effects will be larger. A quantitative effect of the solution hardening can be seen in this diagram. Here we see the yield strength as a function of the zinc content in a copper-zinc alloy. That means that copper and zinc is also called brass. And we can see that when we increase the zinc content, we increase the yield strength. It goes from about 50 to up to 100 when we reach about 30% zinc. Now the difference in size between copper and zinc atoms are not so large. They're rather similar, so this effect is not so strong. If we, for instance, would have tin on this axis, that is, if we would have copper tin, which is a bronze, we would have a much steeper curve like this. An even stronger effect we will get if we go to a system that looks like this. Here we see that the alloy element atoms, they have been squeezed into positions between the atoms in the mother lattice. They have the so-called interstitial positions. We can also see then that they actually destroy the symmetry of the crystal structure quite strongly in this region. And it becomes very large stresses around these atoms. In the other systems we looked at before, the alloy elements substituted the alloys in the base metal lattice. But here they are so small so that they actually can fit in here. But then instead they cause this rather big disturbance. A very important system, which is an example of this, is the iron-carbon system, that is steel. Here the carbon atoms fits in like this between the iron atoms. And in that system, very small variations in carbon content have a very strong effect on the hardness. Only between 0 and 1% carbon, the strength can go up very strongly. So the effects from this type of interstitial atoms are much stronger than the effects of substitutional atoms.